We're going to do a buffer calculation now. Basically, it's a buffer, showing how a buffer works calculation. So I'm just going to show you the slide that this kind of comes off of. So what we're describing here is, here's the buffer. So we already know it's a buffer because we've got the acetate ion and the acetic acid. So we already know we have both. And we're going to do this first calculation in detail, and then the second one, we're going to just kind of show how you would get the calculation from that. And this is going to illustrate how a buffer works, and then you can sort of see how capacity and such kind of comes from this. All right, so let's go to the first part of this. Now, we have made this problem slightly easier because we're going to use the whole solution. So let me just make a note of this real quick. Note how much buffer is used. That's important. You're going to work in moles. Why? Because if you mix a little bit of buffer with a lot of impurity, it's going to have a completely different result than if you mixed a little bit of impurity with a lot of buffer. You know, you can kind of see a lot of buffer would have a better buffering ability than only a little bit. So you must note the volume of the buffer that you use. Otherwise, you're going to have a problem. So in the question, we're going to use 1 liter of a solution that is 0.1 molar, and I'm going to be lazy and leave the zeros out, sodium acetate. And once again, here's my abbreviation for acetate. And it's going to be 0.1 molar acetic acid. Now, if I didn't use the whole liter, say they told me I'm going to take 500 mils of it, or 400 mils of it, or 200 mils of it, or whatever, what you're going to want to do then is use whatever volume is given that you're going to take. The question will normally say something like, to such and such mils of this buffer, such and such impurity is added. So look in the question for that specific number given. Here, since it doesn't say anything, if it just describes making up a buffer and then starts talking about putting the impurity in, then assume the volume is the entire volume that you were given at the beginning of the question. So it's a matter of just reading the question carefully. So here I'm saying I've got a liter of this solution, and I'm just going to dump my impurities in it. If I took half of it, then it kind of makes sense that I'm only going to have half as many moles of each of these things. So let's see what we've got here. We've got 0.1 moles of, and let's think about it really. Do we care about the sodium ion? It's a spectator ion. So really, we've got 0.1 moles of acetate. We've got 0.1 moles of acetic acid. That's what we do by, starting with figuring out how much we have of our buffer. Now what we're going to do is we're going to add the impurity, and in the case that I've done, I did it in such a way to make it so the volume wouldn't change. If there is a significant volume, so if the impurity added has a volume, so include volume if necessary, or consider volume if necessary. We'll say if necessary. In some cases you have to, in some cases you don't. But you're going to now add your impurity. So, for example, if they say I'm adding 2 mils of, let's just do this as an example, 2 mils, 0.1 molar NaOH, extra impurity. Right? So here you'd need to think about that there's 2 mils of that. So that's what I mean by considering the volume. So in my case, what we're going to do is we're going to cheat, and we're going to have 0.1 or 0.01 moles of HCl, but we're going to use it in gas form. So we're going to bubble it through or something like that. So I did this just so that I wouldn't have to think about the volume. I'm just making a quick step. Now the other part of the table is 0.01 moles of sodium hydroxide, and that conveniently is a solid, so we could just plop in a few pellets. All right, so let's go through the process of what happens. What we need to do is identify if the impurity is an acid or a base. And this might sound pretty trite, but here's how it works. If the impurity is an acid, then it reacts with the base in the buffer. If the impurity is a base, then it reacts with the acid in the buffer. Acids react with bases. So there we go. So if the acid, it's going to react with, now we go up here, which one's the base, which one's the acid? Right, this one's the acid, and this one's the base. So This, if it's an acid, is going to react with acetate. If the impurity is a base, it's going to react with the acid in the buffer. So that's the other thing we need to identify, is what reaction is going to happen. Because what we're going to do now is write out a rice table, but it's going to be a limiting reagent problem more than anything else. So let's write out our reaction. In this case, we're going to start with the 0.01 moles of HCl. So HCl is an acid, and we already decided it reacts with the acetate. So here we go. We're going to have acetate. You can include the sodium ion if you want to, but it'll just go along for the ride. It's a spectator ion. So now we're going to have our HCl. This isn't a Ka or a Kb or anything like that. This is an acid-base reaction. These are not related. And so what we're going to make is this, HAC and chloride. So if you had a sodium ion, it would be with this, and then it would end up with this. So we just go along for the ride. So here's my R. Then we do Ce. Okay, so going to the information we have in the question, going back up here. All right, we've got 0.1 moles of acetate and 0.1 moles of acetic acid. So let's go ahead and fill those in. So we've got 0.1 moles down here. And you might write on here, this is moles. You know, you've done a lot of things in molarity, so just do something to remind yourself. You don't need to keep writing moles everywhere. And let's go here. We're going to have 0.1. Maybe these aren't the same. Maybe one's 0.1, one's 0.2. Look at your volume of your buffer and the concentrations of the pieces in your buffer to find that out. All right, so now let's think about what else initially. We are just about to mix these together, so this hasn't been made yet. We haven't had a chance for it to react. We're literally about to put them together. And so now let's look at what we've got. 0.01 moles of HCl. So that's what we're starting with. And it's a limiting reagent problem. This isn't an equilibrium sign here. This is a, goes 100%. So what we do is we say, right, which ones run out first? Well, it's pretty obvious here, isn't it? That one goes away. And of course, this is still C for coefficient as well as C for change. So if this is going down by that much, so is this. And this is going up by that much. And so is this. So that was easy, wasn't it? There's no X in there. So this is going to become 0.09. Be careful with your math here. I've done it. This is 0. So that's all gone. So hey, look, it dealt with the impurity. And then this has gone up. So this is 0.11. And this is 0.01. Do we care about this? It's a spectator ion. Who cares? We know how much we have, and now we don't care. So it's interesting to notice you can actually see the buffer working right now if you just look at a couple of things. Let's just do some circles. Look what we have to start with, 0.1, 0.1. These are the two pieces from my buffer. Now look what's happened. They've become slightly different, but notice how it works. This one's gone down, but this one went up by the exact same amount. That's kind of the key thing to what happens. And that's why the Henderson-Hasselbach equation is so handy, because it kind of just focuses in on that. So now we can go and write the Henderson-Hasselbach equation out. HH. I'm not going to write that whole thing out. All right, so pH equals pKa plus log base over acid. All right, what's base, what acid? Don't forget, this is for the buffer, so it's the conjugate acid-base pair. It's got nothing to do with the impurities. So the base here, if we already go up there and look, is your acetate, and there's the acid, HAC. So here we go. This is going to be my acetate, and this is going to be my HAC. Now, technically, these are supposed to be concentrations, but this is all in the same container. So actually we can cheat, and we can just use moles here and here, simply because there's one concentration divided by another concentration. So this is the other nice thing about using Henderson-Hasselbach. We don't have to go back and turn everything into molarity, and then set up the Ka expression, and then solve and ignore the X's and all the other stuff. Henderson-Hasselbach just kind of notes that we kind of do the same thing every time, so let's just jump, cut to the chase. All right, the only other thing we're going to need is pKa. Well, that's the negative log of Ka. Well, you've written this a whole bunch of times. It's 1.8 times 10 to the minus 5 for acetic acid. You kind of end up almost memorizing that. So there's my part there, and that comes out to be 4.744. Here's a hint: when you do these types of problems, throw in a couple of extra decimal places. Don't trim it too far back, because you never quite know what's going to happen here. So, you know, I might even put another one on here if I were you. So now let's look at this other piece. A little bit untidy, but let's do the plus. All right, so the log of the base over acid is going to be log of. Now, this is, you can use this before we put in the impurity or after. Before the impurity, these were both 0.1. So look what happens. If these are both 0.1, they cancel. The log of 1 is 0. pH is pKa. Very handy to remember that. But it's no longer equal, so let's go to the actual concentrations that we have. Acetate is 0.09 and acetic acid is 0.11. So we put those numbers in and we're going to do our negative log of that. And, oh sorry, not negative log, just our log, and that comes out to be minus 0.087. Okay, yeah, be careful. This is a plus, and it just happens when you take the log of it, that becomes a minus sign. So this is actually going to drop this down a little bit from 4.744, but let's see what it's going to end up being. All right, so here we go. What we end up with is 4.66. Now, let's actually return to what we had before. Before, because she's listed in the table, but I'm going to go ahead and give it to you here. Before, the AC minus was equal to the HAC in this particular buffer, and it was equal to 0.1. So the pH equaled the pKa, which was 4.744. So what are we noticing here? All right. Clearly, this is not exactly the same as this, but it's also not that far different. I mean, if you kind of look at, you've dropped about a little bit less than 0.1 pH units. So dropped less than 0.1 pH units. And think about this for a second. I'm putting in 0.01 moles of HCl. That's still quite a bit. You know, if you're doing this in an experiment and you're doing your experiment carefully, you really shouldn't have that much crud falling in your experiment. So it's probably more realistically going to be a smaller number than 0.01. It might even be another couple of orders of magnitude smaller. So then if you think about it, these changes become even tinier compared to the original values. And so that's why buffers seem to not change. It's because this ratio got slightly adjusted, but not drastically. So it started off being 0.1 over 0.1, and then it went to 0.09 over 0.11. So you can imagine if you went with an even less number of moles, it would be even more like still being 0.1 over 0.1. One would be slightly less, one would be slightly more, and that's how buffers work. You can play with that on your calculator. Try that. Try actually making the above table so that instead of it being 0.01, it's 0.001, and you'll see what I mean. You can try that yourself. So this is the setup to calculate what would happen as a result of putting it in. Now the checkpoint that you can always use to help make sure more your math's okay. I put in an acidic impurity. The pH isn't going to not change at all, and it will go down, just not by very much. And the reason it goes down is because it's an acidic impurity. So it did go down, so this is consistent with an acidic impurity. All right, now, how would this work for a basic impurity? Same kind of idea, so let's just kind of cut back to the table a little bit. Let's say we put the NaOH in. That's a basic impurity. So we've got 0.01 moles in that table. This is the second kind of part of the problem. 0.01 moles in there. So what is NaOH going to react with? Well, it's going to react with the HAC, not the acetate. The acetate is itself a base. So we're going to have the sodium hydroxide impurity react with the acetic acid in the buffer, so we can write out a calculation for that. I won't go the whole way through the table, but we'll start the process going. So it's going to be HAC plus sodium hydroxide. And once again, goes completely to completion. Now we're going to make sodium acetate, and we've got water here. All right, so again, returning to this original buffer, we had 0.1. This is all in moles again. This is 0.1 moles, This is 0.01 moles, and this is 0.1 moles. So you can see what's happening. It's going to look basically the same as before. You can see that this is going to go down by 0.01, etc., etc. So this is going to go to 0. You know, you can kind of see how this is going to work. This is actually going to go down by 0.01. Let's go ahead and fill it in. So this is going to become 0.09. This is going to go up by 0.01. So this is going to go 0.11. Now that might look like the numbers we had before, but remember the reaction last time was this one. It was acetate reacting with an acid to reform the original acetic acid. So this time we're taking the acetic acid, getting rid of some of it and forming the salt. So now it's gone the other way. So if you go up to this relationship here, all that will be different is instead of it being 0.11 over 0.09, it'll be 0.09 on the bottom and 0.11 on the top, because the base has gone up now. See, the acetate has gone up and the acetic acid's gone down. So the pH is going to be, I'm going to just put the number in, 4.744, because it's still the negative log of the previous, it's still the same Ka we're using, and it's going to be the log of 0.11 over 0.09. And so what you end up with is, instead of it being minus 0.087, it's plus 0.087. In other words, less than 1 pH unit increase. So once again, put in a basic impurity, the buffer, its pH does go up, but not by much. That's the buffering action.